So, engineering analysis involves understanding the relationship between two or more variables. Okay, that's on the front of you. That's on your handout. Yeah? These slides are what you've got. Okay? Understand the relationship between two or more variables. For example, relationship between two variables can be established by plotting a graph between the variables x and y, time and velocity, time and temperature, distance, speed, etc. Okay? So we're going to be looking at various functions that we might, in most cases, be able to plot in some kind of graphical form as well. Come on, Daniel. All right. So, moving on again. Got a little drill for you. Can't remember if it's over 1 or 2 pages. Yeah, 2 pages, I think. The next 2 pages, a little bit of a drill on things you might already know. So, just 5 minutes. Have a go at those. Okay. Then we'll come back to that, and I'll explain and fill in any gaps. Right, gents, let's have a look, see what we know. Big mass, what does it mean? Anyone like to offer me an answer?
Brackets.
Brackets, yeah. Yeah. Brackets, indices, division, multiplication, addition, subtract. More formally, they are the laws of precedence. So they define, that's a little acronym for you to remember the definition of the order in which you do mathematical operations. So we do anything in brackets first. Inside the brackets, we follow the same rules. So if there's another set of brackets inside a bracket, you do them first. And then you go in the order of, you deal with indices first, then division, multiplication, then add and subtract. And you do need to be a little bit careful with, modern calculators are pretty good, but there are some little pitfalls if you're not careful. For instance, if you do straight minus 3 squared, you'll get the wrong answer. Because what is the answer to minus 3 squared? 9. Now do it on your calculator. Yeah, because what the calculator is doing 3 squared first, and then multiplying by minus 1. So what you need to do is put the minus 3 in brackets and then square the brackets. So just be aware of that. Alright. Other pitfalls are when you've got an expression like this over an expression like that, that line all the way there they never put them, but it implies brackets around this. It's all of that divided by all of that, and you can come unstuck there with a calculator if you're not careful. The easiest way round that problem is to use the fraction button, so you actually create a fraction on the modern calculator. Alright? So, standard linear equation. Which letter represents the independent variable? Yeah. And you're right. It's the one that isn't being controlled by something else. Yeah? So it's, in this case, x. So the dependent variable is y, yeah. Y is equal to a function of x. Yeah. So y is the one that's going to depend on what the value of x is. Alright, we might change that round and say what value gives me a particular value of y, but y would still be the dependent variable there. Okay. What does the letters M and C represent? M is the gradient or slope, and y is the C, sorry, is the y intercept of y-axis. So graphically, changing C up or down moves the whole graph up and down the y-axis, and if we alter M, if we increase it, the slope gets bigger. If we decrease it, the slope gets smaller, and if we make M negative, the slope goes in the opposite direction, down instead of up. Okay, so that's that first page. Right, let's have a look at this one. Write the number 32,682 in standard form. Anyone going to offer me an answer? Not quite, no, but good effort. 3.2682. Yes. 3.2682 times 10 to the power of 4. The decimal point in that number is there. And by putting a positive power in, we're moving that 1, 2, 3, 4 places to the left. Yeah. Standard form is a number between, a digit between 1 and 9, then the decimal point, and then a power of 10 at the end. Any power of 10. What about the number 0.323 in engineering form? So as a derivation of standard form. Similar to standard form, but as an extra qualification on it. If that was 0.323 amps, what also could I say? 323 milliamps. But in engineering form, you'd write that as 323 times 10 to the minus 3. So in that form, that would be milliamps. When you moved it to engineering form, that becomes amps. If that was milliamps, then that would be defining it in amps. Okay, and in science we'll look at how that's quite important, because if you're using, for instance, Ohm's law, you can't have your voltage in volts and your current in milliamps. You've got to have them both in the same multiple, and so writing it like that would help you get around that problem. And engineering form is 1 to 3 digits before the decimal place, and then the powers of 10 are always multiples of 3. So we can go milliamps, microamps, and so on, and we can have kiloamps technically, and megaamps, more like megavolts. But we can go so that, but the powers of 10 are always multiples of 3 or 1,000, or divisions of 1,000. Okay? So if we convert, how do we convert 3,268,256 watts into megawatts to 3 significant figures? Well, first of all, let's put some commas in here so we can see. Yeah, you've got 3.268. Anything else? Is that the 3 significant figures? 1, 2, 3. Yeah? So what we got to do, 2, 7, yeah. Okay? And that's something that you're going to have to get used to being, choosing an appropriate number of significant figures to round your values to. Okay? And that's particularly pertinent when you're doing experimental work and you're doing calculations with measurements that you've taken. There's no point in reading an oscilloscope voltage to 2 significant figures, multiplying it by something else and quoting your answer to 4, 5, 6 or 7 significant figures. Alright, so you need to learn how to be appropriate. What is the answer to 3x minus x? 2x, yeah. That's put there because sometimes there's a mistake that some people will say the answer to that is 3. But that is 3 times x. Take away one of those x's, you've got 2x. Alright? What is the answer to this? Yep. 2x squared plus 3x, i.e. we multiply everything in the bracket by what's outside the bracket. Yeah. Three x squared plus 6x, how could we rewrite that? No. Plus. So what could we do with that to simplify it? Yeah. X to the power 4 times x to the 2. Yeah, x to the power 6. It is this law of indices, and we're going to look at it a bit more detail later today. But it's x to the 4 plus 2. For multiplication, we add the indices. Yep. Y to the 6 over y to the 2. Y to the 4, because it is y to the 6 minus 2. And we divide indices with indices, we subtract them. Of course, the variable that you're doing that with has to be the same variable, both y or both x, or both z or whatever quantity we're looking at. Okay, so that's just a little drill. Anyone got any clear worries about any of those aspects? Because they're all things that you may well have done before on BTEC or some other engineering course, even if it's a long while in the past. So, but we're going to have a more detailed look at most of those aspects anyway. Right. So we change, or we control, or we state what one variable is, the independent variable x, in a mathematical expression, and we observe how changing that affects another variable, the independent variable y. We're going to be looking at linear relationships, such as this. Y equals mx plus c, with that being c, slope of that thing being m. Okay, if we make m negative, slope will go that way. Okay, the other two that we'll come across in this module are ones like this: a parabola, which is a quadratic, depending on how we choose the variables, the constants, it might open upwards or open downwards. Okay, and it may or may not have what's called roots. values of x where y is equal to nothing. And again, we will be looking at that and determining roots of quadratic equations. We also may well come across cubic functions like so, which may or may not have a point of inflection like that one. They'll have an x cubed term, cubic. Okay, the quadratics, by the way, have got an x squared term in. Okay, we will, on this module we won't be going, I wouldn't have thought, beyond cubic, but we will touch on sine, cosine, those trigonometrical cyclic functions. All right. So we're going to just look through this problem, not going to actually draw these graphs or anything. If a graph suggests there is a relationship between two variables, we can look and try and find a function that fits. We kind of do a lot more with that on the second year maths module, trying to fit a function to some experimental data. So we can try and find a function that fits that data, and what we're essentially doing is finding an equation of a line. For example, the equation of a straight line is a linear relationship. Y equals mx plus c would be the form of that, where m is the slope and c is the intercept with the y-axis. So looking at this problem, following values of resistance R, ohms, correspond with voltage V, obtained from a test on a filament lamp. There's some data there, okay, and that example asks for that to be plotted, which I've now done on the next page. So that data is plotted in autograph software, actually, okay, so that we can see. You then connect the data points to the best fit line. Doing that is called interpolation. You're connecting those points with the best fit line you can find. Okay? So what that means we can do is look at this graph between the points and find a value for current when the voltage is, for example, 40 volts. We can go up and across. Okay? If we look outside the data points, i.e. we assume that linear response continues on further than our data, either downwards or upwards, that's called extrapolation of that data. You're extending that beyond what you measured, which in some cases could be a risky thing to do. Yeah? Many of the sensors used out in industry, you can often find they've got a linear relationship in the middle of their range, but it can go quite a way away from that out at the extremes. Yeah? So extrapolation can be a dodgy thing to do if you're not careful. It just depends on the application. Okay, so from that straight line, we can look at the graph and we can determine what the intercept is. Okay, so looking at the y-intercept here, value of resistance when the voltage is 0 is approximately 10 ohms. But value of resistance here is 10 ohms. So that would be our C on the end. The gradient, we'll look for a convenient point to find how much y changes for a certain change in x. Okay, and this is kind of the real first lead into what we'll do when we'll be doing differential calculus halfway through the module, because that's what the differential is. It is the change in y over the change in x. So we find our m by looking for a particular change in y and what is the appropriate change in x. And you guys will remember that probably from advanced maths we did last year. We've done some work with finding gradients, didn't we? Okay. So that's what we could do from some experimental data, find the best fit line, and then see if we can extract from that data information that will give us our constant values M and C for this linear relationship. So using the graph, when the voltage is 60, so the question asked you to use the graph. So find the equation of the graph, which I've talked about, the value of resistance when the voltage is 60 and the value of the voltage when the resistance is 40. And what would the resistance be obtained at 110 volts? So they're kind of going outside. 110 volts is going outside the data, but it indicates around about 148 ohms. When the voltage is 60, resistance is approximately 87 ohms, and the resistance would be 40 ohms when the voltage is 23 volts. Yeah. Okay. And that, I mean, an incandescent lamp, there's quite extreme changes in resistance for the amount of current that's flowing and how hot they get. So that's a viable experiment. So that's kind of a little preamble about functions and the type of things, different functions that we're going to be looking at. I'm going to move on to now is representing very large and very small numbers. We already had a little bit of talk about it, but two methods. One is standard form, kind of the scientific way. That's the one with one number, then the decimal point, and a power of 10. And the engineering form, which is a modified version of that, where the power of 10 is always a multiple of 3. And then we get our millis, micros, nanos, picos, and so on going down, and our kilo, mega, giga, and so on going up. By the way, kilo, capital K is the computing kilobyte, 1024. Lowercase k is the engineering kilo, as in 1,000 watts is a kilowatt. Right? So, standard form represents large or small number with a single digit to the left of the decimal point multiplied by a suitable power of 10. So, 12698 in standard form is 1.2698 times 10 to the 4. If we was to have that in engineering form, it would be 12.698 times 10 to the 3, which is kilo, whatever the units are. Yeah. If the decimal point has to be moved to the right, the index or power 10 becomes negative. So 0.0237 in standard form, we're moving the decimal point 2 places to the right, so it's a power of -2. Engineering form, modified version. So between 1 and 3 digits to the left of the decimal point, multiplied by a sort of meters in engineering form would be 12.698 times 10 to the 3 meters, or we can say 12.698 kilometers. When it's in the power of 10, the units are the SI base unit, meters. When we say kilo, that's what we're doing with that. Right? 0.0237 amps, 23.7 times 10 to the minus 3 amps, or it's 23.7 milliamps. And then we've got our prefixes, tera, giga, mega, kilo, they're all the ones above 1, milli, micro, nano, pico are the ones below. Alright, on your, if you've got the Casio calculators, and most people who come here do, there's an ENG button on the calculator which will convert a number in standard form to the nearest engineering form. So if you put, you need to get an answer really, but if you got an answer that was like 2.37 times 10 to the minus 2, pushing that engineering button will take that to the nearest valid engineering form. And if you keep pushing it, you can make it go up or down, engineering forms in steps in powers of 10 to the 3. Okay? Yeah? So, what I'd like you to do now is complete that table.